Okay, we're going to continue with 10.5, and now we're moving on to the equations of planes. Your equations for planes, we're going to focus on the scalar equations. For a plane, a vector does not define a plane. Okay, so a vector in the plane doesn't define it. I can't tell you, the equation of a vector, and you would be able to pinpoint which plane it's in. A good example, we often use a room to represent, your 3D coordinate system. Well, if I said I'm looking at this right here, the line that's where the wall connects to the floor, I'm looking at that vector. Which plane is it in? Well, it's in more than one, right? I mean, if this most basic example, it's in the plane of the wall and in the plane of the floor. I can't determine it. Okay. However, a vector perpendicular or normal, okay, same when we're talking about vectors, usually use the word normal instead of or when we're talking about planes, we talk about a vector normal to the plane, not perpendicular. Okay. A vector normal to a plane does define it. Okay, which seems kind of weird, but if I said, I'm thinking about the vector that's coming straight out of the floor. Okay, well, there's only one plane that vector is perpendicular to, and it is the floor. And remember, position doesn't matter. So the floor and the ceiling, that's the same plane. Okay, so that's kind of a weird little nuance that a lot of times we care more about the normal vector to the plane than any vector that's actually in the plane, because that defines it better. Okay. Your equation is kind of derived from the whole idea that if two vectors are orthogonal, their dot product is 0. So if we have R is an arbitrary point in the plane, oops. Okay, and maybe R is the position vector of an arbitrary point in the plane. Okay, so the position vector of R is just x, y, z. Okay, those are your variables, right? R naught is a known point in the plane. Okay, so that one will have specific values for it, and we'll call it x naught, y naught, z naught. Okay, then R minus R naught is a vector in the plane. Okay, so we would have x minus x naught, y minus y naught, z minus z naught would be a vector in the plane. Okay, so that means that the normal vector here, a normal vector, okay, so then what we know must be true is that n dotted with r minus r naught has to equal 0. Okay, because they would be perpendicular to each other. Another way to do that is with your properties of dot products of vectors. Be like this. Okay. So in general, though, we want the scalar equation of a plane. That's the way that we see it more often. So the scalar equation of a plane, we would have the n, let's see, vector n, I think your book uses ABC. And then we have r, which would be x, y, z. And then we have r naught, which is x naught, y naught, z naught. So when we perform that dot product, we would have a, b, c dotted with x minus x naught, y minus y naught, z minus z naught, and that would equal 0. So a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. And that's the way that you're going to see equations of planes a lot. And it's very easy then to pick out the normal vector by looking at the a, b, and the c, and a point that's on the plane by looking at your x naught, y naught, and z naught. Okay, let's do an example before we get too far ahead. I'm going to leave some of the more difficult examples for us to work during class, talk a little bit about some of the hints with them. But if we look at example 5 in your book, okay, so in example 5, it says find an equation of the plane that passes through the points P, which is 1, 3, 2, Q, which is 3, negative 1, 6, and R, which is 5, 2, 0. So we want the equation of the plane that contains those points. Okay, so remember, we need two things then. We need R naught, which is the position vector of a point on the plane. So we've got 3 of those that we could choose from. Okay. And then we need n, which is the normal vector to the plane. So that's going to be the trickier one. Okay. So that one we have to figure out. Okay. So we're going to use the fact the cross product of 2 vectors gives a vector orthogonal, perpendicular, normal, right, whatever, to both. So all we need to do is use those 3 points to come up with 2 vectors in the plane and find the cross product. Okay, so we can do your vector PQ, right? So from P to Q would be 2, negative 4, 4. We can use PR, which would be 4, negative 1, negative 2. We could use QR if we wanted to, which would be, let's see, 2, 3, negative 6. Okay, we can use any of those we want, and you could switch them around, like QP would just be the same as PQ, but negative, doesn't really matter. So we just need to pick 2 of those and find the cross product of them. Okay, so we'll take our I, J, K, we'll take our vector P, and our vector PQ, and our vector PR. And again, it doesn't matter, you can pick any of them. Okay, and we're going to do our cross product. So for I, we'll have negative 4 times negative 2, which should be 8, minus negative 4, which should be 12. And now we have to subtract. For J, we'll have negative 8 we'll have negative 4 minus 16, which would be negative 20, minus negative 20, so plus 20, J. And then for K, we'll have negative 2 minus a negative 16, so negative 2 plus 16, which is 14. Okay, so there's your normal vector. Okay, so now what we can do is remember we will have a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. And for A, we have 12. For B, we have 20. And for C, we have 14. x naught, y naught, z naught can be any of our points. So if we just use point P, we've got 1, 3, 2. Okay. One thing, well, here, let's finish it. Okay. And I'll show you, because a lot of kids are like, well, won't that change if you use different points? And we'll do this again. Actually, I want to keep this short. The answer is it won't change. Okay. So I would go ahead and encourage you to try with maybe PR crossed with QR and point Q. Maybe we'll do that in class and just kind of show that it's the same. Okay. But then we can go ahead and distribute this. Okay, so we'd have 12x minus 12 plus 20y minus 60 plus 14z minus 28 equals 0. So we'd have 12x plus 20y plus 14z equals, what are we going to have on the other side? 100, right? Yep. No, 90. Oh, 100. 100. Okay. And that's how you're used to seeing equations of planes. That's when you did in Algebra 2, when you first learned your three-dimensional coordinate system. That's what planes look like. We do know we can scale them down also, which is pretty good practice. So 6x plus 10y plus 7z equals 50. Okay. And do notice that those coefficients there are your normal vector, right? The 12, 20, 14, or scale it down to 6, 10, 7. So given the equation of a plane in this form, you can easily pick out the normal vector. Okay. A couple of things in example 6 in your book. Okay. They make some big jumps there that you kind of have to wrap your brain around. The first one is find the angle between two planes. Okay. The angle between two planes would be the same as the angle between their normal vectors. Okay. So you got to kind of wrap your head around that one. If you're finding the angle between two planes, you can also just find the angle between their normal vectors, and that would be the same thing. And the reason that we might do that, again, is because it's so easy to pick out the normal vectors. The planes that they give you are x plus y plus z equals 1, and x minus 2y plus 3z equals 1. So your normal vector 1 would be 1, 1, 1. And your second normal vector would be 1, negative 2, 3. Those coefficients, remember, give you your normal vectors. So you're just finding the angle between those two vectors using your cosine theta equals the dot product over the product of the magnitudes. Okay. The second thing that they have you do is find the equation of the line of intersection. Okay. The line of intersection of two planes would be perpendicular to both the normal vectors. Okay, so that's another thing that we can kind of talk about in class a little bit more too. But kind of wrap your brain around that. The fact that if we looked at the intersection of two planes, that line would be perpendicular to the normal vectors of both the planes. Okay. So, and then example 7, another one that we'll kind of look at in class more. Find the distance formula between a point and a plane. So you need to think about, if I can take a known point on the plane, okay, and I want to find the distance between another point and the plane, the distance will always be perpendicular, right? So what they do for that is they say, well, look at this vector. The projection of this vector onto the normal vector to the plane would give us that. Okay, So they find the component onto n, they call this one vector b, and they find the magnitude of that. Okay. So again, those are some a little bit more advanced ones that we'll use our work time in class to go over, to make sure you at least have a good grasp on example 5 for now.